Okay, hi everyone. Today we are going to learn measures of location. So the title is more general, but basically what you're going to learn is kind of averages. So like average and its variance. Okay. In the first two chapters, we learned probability and conditional probability. Probability is definitely the most fundamental uh, building block in statistics. But basic purpose of learning probability is to describe, summarize, and represent the randomness. But probability is like okay, but it is not that convenient to use. So we usually use on average to describe data, right? Like in sports, you are curious what kind of how good a player is. Say then in football we say average carry per average yard per carry or like average yard per game, things like that. So so average is more common measure to summarize and represent data. And there are some variants and alternatives to the average. So we are going to learn them in this chapter. So basically, you may understand that there are two major, most commonly used methods to summarize and like describe data. One is probability, which we learned in the first two chapters, and the other is average and variance. So, even the most advanced statistical methods can be, roughly speaking, can be described as some kind of probability or average or combination of them. Okay, so these two are the most important things. And of course, in the textbook chapters, you can just find average as a keyword. Before defining what is an average, I first introduce a new concept, right? So let me start with an example. Suppose that you have data on used car, and you have five variables in the data: listed price, the make and model of the car, and the model year, and the mileage, and the number of major repairs. So for each car, we observe them, and we would like to summarize the average of the used cars, and then one variable cannot have an average. What is that? It's a quick question. There is no trap. The answer is B, the make and model. The others like listed price, model year, mileage, and number of repairs are numbers, right? So when the outcomes are numbers, you can calculate the average, and you can compare them, which is great. And you can order them, and you may compare them. And the average between 1 and 2 is 1.5, things like that. So, however, that's a we can it is easy to calculate the average if you have numbers. But the make and model, like Toyota Camry or F-150, it's like 150. It's not a number. It's just a name, proper name. So we do not have numbers to calculate the average. So we have to distinguish these two different types of variables. The make and model, this variable is called categorical or qualitative variable. It is just labels, just groups, different categories, right? Like Ford, Chevy, or and like you cannot calculate the average between Ford and Chevy. What is in between them? There is no like numerical comparison, numerical addition of these two, so we cannot calculate the average. But the others, numerical variables or quantitative variables, have no difficulty. As long as you observe them, then it is easy to calculate the average, right? So we are going to consider numerical variables only, or we are going to like think about the numerical outcomes only, right? Or you like so uh, then you can calculate the measures, some measures based on those numbers. The variable needs to be number, right? For example, when you calculate the average, or when you calculate the maximum or minimum, to calculate the maximum or minimum, you should be able to compare which is greater, which is smaller. But only you may compare numbers, but like as I said, you cannot tell like Ford is greater or like Chevy is greater. It's impossible. And variance and standard deviation, you must have heard about them. They are also numbers, and median and percentiles. In case you know what they are, then it'll be easy to understand why the outcomes have to be numbers, right? So we are going to restrict our attention to numerical variables. Otherwise, we cannot study the average here. Okay, so like in most cases, actually, the outcome may not be a number. Like for example, coin toss. Coin toss is heads or tails, but still you may put numbers on them. Like heads is denoted as 1, tails as 0. That is also possible, right? But most cases, the outcomes are naturally numbers, like dice roll, YouTube video count, and like stock return. Those are naturally numbers, so we don't worry too much about the restriction, right? So most of the variables we are interested in are numerical, so we don't worry too much. And also, you should be careful when you try to analyze non-numerical variables. You have to worry about if they are actually numbers or not. And also, we are going to need notation. So in first two chapters, when we define a probability, I told you that the probability is a function assigned to an event. And an event is a set of outcomes. So, like the first two chapters, we are based on kind of set theory. I did not say much about numerical operations, right? So it was more like union, intersection, complements of the set. So those are the probability was a function for sets. But now, as I said earlier, now we are handling numbers, not sets. So we are going to basically we are going to maintain the same notation, but let me mention that here. So our random variables are going to be denoted as capital letter X, Y, Z, usually X or Y or Z. And probability will be based on the number and on equality or on inequality, right? So for example, this is probability that random variable x equals to a specific number, small lowercase x. Or this means probability that a random variable y is smaller than or equal to a specific number, lowercase y. So here, the uppercase letter is random variable. It is variable. It is not realized. It is like it can be anything, right? Because it is random. Like when you roll a dice, like for example, think about this. Probability that the number on the dice, the outcome from a dice roll equals 6. This is how we talk about probability. But in this structure, first, probability is defined on this event, the event that the number from the dice equals 6. But this sentence, this event, is composed of the first part. The subject is the outcome from a dice roll. This is random variable. So the outcome from a dice roll can be any number from 1 to 6, right? So it is not yet realized. You don't know what's going to happen. It is like anything is possible, right? So this is uppercase letter. But when you define probability, you have to specify the cases. Like here I'm interested in like the outcome from a dice roll can be any number from 1 to 6, but I am specifically interested in 6. You have to specify the event. That in this case is 6, so I'm going to denote that as lowercase letter. So again, when you define a probability, you need an event, and when you define an event on a numerical random variable, you are going to use equality or inequality. Then when you use equality and inequality, you need to have two sides, and one of them must be random variable, which is unrealized, can take different values, and on the other side is a specific value. It is not a random outcome. It is just what you are interested in. Like I say here, 6. 6 is just where you are interested in, and the and we are going to distinguish them by uppercase and lowercase letters. Okay. And when obvious, I'm going to use just probability of lowercase x only, because most cases just the random variable I'm referring to is obvious, right? I keep seeing the same example, dice roll, then you know the uppercase letter is dice roll, then I will simplify the notation like this. So then it may look like a function of a number 6, like 6 here, but actually probability is a function of a set, just this part is hidden. It's a function of event, and the event must include some inequality or equality. And furthermore, that when you roll dice like multiple times, 100 times, then you have to imagine 100 different, possibly different outcomes. So then we are going to denote them as subscript, index them by their subscript, right? X1 is the dice roll, the outcome from the first dice roll, and if you throw it second time, then you get outcome X2 and X3. So even before observing the outcomes, even before the outcomes are realized, you can still denote them mathematically like this, right? And this is exactly the data we are handling, right? So our data looks like this. We observe repeated experiments, so we are going to observe n number of outcomes. So that is data of sample size n, okay? Okay, then here is an example. Like suppose that like our department awards the best graduating undergrad student. The name of the award is Golden Carp Award. Like it's graduated to the best GPA, or I don't know. I'm not in the committee, but anyhow, there is a committee who selects students for the award, Academic Excellence Award. So think about that. There are two candidates for the award, and suppose that two students took 10 economics classes, and this is their transcript. Like student 1 got these grades from 10 different courses in economics, and student 2 got this. And we would like to compare them, but they are not numerical, right? So, like, it is not easy to compare who is better. Like, it's not easy at a glance who is better. So, like, we are going to transform them into numbers for more convenient manipulation and comparison, right? So you know how to convert the grade, right? So actually the conversion is kind of arbitrary. It's just convention. I don't know why like say A and A minus must be zero point 0.3 differential, but A minus to B plus is 0.4 differential. I don't know, but that's just common convention. So I'm following that. That means now the outcome is numerical. This is how we make like numerical variable. So okay, then it's better. Now we have some room for manipulation and some operation, like like still, so we get 10 numbers for each student. It's not easy to see who's who's better, right? The higher the better, but 10 numbers are not that informative. Hard to tell who is better. So again, we change it to the frequency distribution table. One more manipulation. So I summarized their grades like A minus, B plus, B minus, and I count the frequency for each student, how many A this student got. Like, so first student got 1A, but student 2 got 3 A's. Like in this dimension, student 2 could be better, but like their worst in both students got their the first student's worst grade is B flat. Uh, Only two in two courses. The first student got B flat, but student two got B minuses in two courses. So in this dimension, student one is better, right? So the lower minimum grade is higher than student two. So still, like this summary, we summarized 10 numbers into like 5 numbers distribution table, like frequency distribution table. Still not clear how to compare them, right? So in the end, for to have a numerical comparison, we need to have just one number for each student, right? So this is a histogram based on the frequency distribution table. So this shows that like student one get one A flat, and student two get 3 A flat. And so the higher graph means that student got more frequent grade, or the corresponding grade, right? Like this. So like for example, student 1 got 0, 2.7, right? So this is a histogram, which we are going to use similar form in chapter 6 or 7. So like usually we use bar graph, but I intentionally use line graph because we are going to understand this as a function later. So I wanted to show that this is actually a function, right? When you enter an outcome, then it returns the frequency. Anyhow, so again, we hope to, so in this function, in some area, blue is higher, but other area, like orange is higher. So hard to compare which is better. So, so like we are going to summarize even further, right? So we will have only one number to represent each student. That is GPA, grade point average, right? So I will explain how to calculate the average later. I believe most of you know how to calculate that. But if you do the average, then the first student got 3.47 and the second student got 3.44. So student 1 is better in terms of the GPA. And we are going to make decision based on the GPA. Then I will give the award to the first student. That is a typical decision-making process in our daily life, right? So basically, if you ask me why we need to learn the average, then my answer is that it summarizes the data in one number. Then, like the power of having one number means that when you have two numbers, you can compare them, which is great, right? So like if you have two numbers, then they may not have like strict inequality, but one numbers, you can definitely choose whether which is greater or smaller or equal. So it helps you make decision. I cannot say it is the right decision, but at least it helps you make a decision easier decision, and more likely to be right, I guess, and also like more objective way to make a decision. Okay, so that's why, in like broadly speaking, uh, this is the role of the average, but basically it doesn't need to be average. You can think about different measure to do that role, right? So that is a measure of central location or central tendency. So by a measure of central location, I mean it is a value around which the data are located and centered around. So basically, we would like to calculate the center of the data, and we may interpret this as a typical or representative outcome in the data, right? So two most common measures of central location is, of course, the mean, which is the average, and the alternative is the median. So if you have heard about this, that it is right, it is that median, but I'm going to discuss the median later in this chapter. Okay, so it was a brief introduction to this chapter, and in the next video, I will start the definition and how to calculate the average first. Okay, thank you for watching. See you later.